Hi everyone, I'd like to wrap up our learning about the derivative by talking about second derivatives. So the idea here would be that if you start with a function and you apply the definition of the derivative, what you end up with is also a function. We call it f prime. So if it's a function, why couldn't we then apply the definition of the derivative to that as well and get the derivative of the derivative? That's called the second derivative of the function that you started out with. And we want to look at that and figure out what exactly it means. And I want you to be aware as well that there's no reason that we couldn't take a third derivative or a fourth derivative and so on. And the idea would be that every time you apply the definition of the derivative, you get a function, and you can then apply the definition of the derivative to that and get a second derivative, and then again would give you a third derivative. So let's get into it. This does start with a little bit of a warm-up. So you should certainly be able to work a little bit on part A and part B as a warm-up. So pause and look at that and then jump back in with me and we'll start into the second derivative business. Okay, so we are given the graph of a position function. So we are looking at the position of a car measured in thousands of feet as a function of time measured in minutes. And we're supposed to describe what is happening to the velocity of the car. So remember, velocity is speed with a direction, so it can be positive or negative, and it's related to the position function because it's the slope of the tangent line. The instantaneous velocity is going to be the slope of the tangent line. All right, so if we're looking at this graph, we start off with very, very shallow slopes to our tangent line. I think it would be possible to be even saying, I think we're starting off with the slope of 0. We are looking one-sided there because the graph does dead end, but we can still kind of get an idea. That means we're starting off with a speed of 0 or very close to it. As we head through that first interval from 0 to 4, the tangent lines are just gradually getting a little bit steeper, not a lot steeper, a little bit steeper. So over the first 4 minutes, the velocity of the car is slowly increasing. The car is going faster. From 4 to 8 seconds, the slopes of the tangent lines get, I don't know, I think they make a little bit of a jump. They get a fair amount quicker, but then they hold pretty steady. This looks almost perfectly linear. So it looks to me like the slope is staying fairly constant throughout that interval. So I would say now we've reached a maximum speed and we're just holding that velocity over that 4-second interval. Maybe right at the beginning and right at the end, we're still coming up to speed or just starting to slow down, but that's what I see in the middle. And then from 8 to 10 seconds, where does that end up? Right here, our tangent lines start to get a little bit less steep. So this is the car slowing down, and I said seconds, but it's minutes. So for minute 8 to 10, the car is slowing down. And then over the last 4 seconds, 10 to 14, this has a slope of 0. So this is where a lot of people would be tempted to say that the car is holding a constant velocity. I guess that's true, but that constant velocity is 0 since the slope is 0 throughout that entire thing. So the car has now come to a stop and is not moving during those last 4 minutes. So that's what I'm seeing on the picture. In part B, we're asked to sketch a graph of the derivative function of s prime of t. We've just described the slopes fairly carefully, so let's summarize that and then try and translate that into y values on the grid below, the left-hand grid. So we said that we started with the slope somewhere around or very close to 0, and then our slopes were positive and they were increasing a little bit as we went. The line was getting steeper. And then as we get to t equals 4, and then all the way through almost to almost to t equals 8, our slopes are still positive, but we notice that they're now constant for a little bit. They're not increasing. Our slopes are not increasing. Our y values are, but our slopes are staying fairly constant. Then from 8 to 10, Slopes are still positive, but now they're getting smaller. They're decreasing. And somewhere around 10, or maybe just after that, it looks like our slope becomes 0 again, and then it stays 0 all the way until 14. Okay, so we need to then translate that into y values down below. So we're going to start with a y value of 0. After that, our y values are positive and increasing, positive and getting bigger. Generally, I don't want to get too hung up on exactly what our slopes were, in other words, exactly what our y value should be, but I think for the stretch from 4 to 8, where it looks almost like a perfectly straight line, that might be a nice reference. So if we go back up to our graph and we look from 4 to 8, it looks to me like I go roughly over 2, up 4, over 2, up 4. So that piece where it looked like my slope was staying fairly constant, I think the slope is 2, which means down here below, let's say this is 1, 2. At t equals 4, we should be getting at least close to, if not right at, a y value of 2, and it should stay right around 2 all the way up until t equals 8, or fairly close to t equals 8. So I'm going to make this maybe a little bit more exaggerated. It's probably going to be curved since we were curved, so maybe something sort of like that, coming up and then leveling off. And then, like I said, it stays level. The slope stayed constant at 2 for that stretch, so our y value down here will stay constant at 2. Then from 8 to 10, our y values were still positive, but they're now decreasing. And right about 10, we expect to get back to 0. So this is going to start dropping down, and then at 10, it's going to get back to 0. And then from 10 to 14, our slope stuck at 0. So down here, our y value should stick at 0. So that's about what y equals s prime of t looks like. Okay. Next, we're going to acknowledge that that s prime of t is really our velocity function, our v of t. So we're renaming that v of t, and I would like to calculate an average rate of change of v and talk about what exactly that means. So let's look at 2 to 6 and 6 to 10. So from 2 to 6, it looks like, and again, this is really rough. I estimated the graph, but I just want to think about a meaning here, so I won't get too worried about that. It looks like we had a y value of 1/2, and then our y value got up to 2. So if we calculate an average rate of change, it's 2 minus 1/2 over 6 minus 2, or 3/2 divided by 4, or 3/8. And I'm even going to go one step further on this one and convert that to a decimal, just because I really want to look at a unit rate, what's happening per minute instead of what's happening per 8 minutes. And let's go ahead and crunch 6 to 10, and then we will explain both of them. So 6 to 10, we're going from that same point, 6.2, down to 10.0. So our average rate of change will be 0 minus 2 over 10 minus 6, which is negative 2 over 8, or negative 1/4, or negative 0.25. All right, let's look at what each of those mean. So remember, this was average rate of change for the function above, which was the velocity function. So this is change in velocity over change in time. And let's go back and make sure we're clear on what the units on that velocity function were. So remember, up above, we had thousands of feet and minutes. So when we make the derivative, this is still minutes. The x-axis stays the same, but the y-axis is now slopes from that original function, which will be thousands of feet per minute. So the y-axis is now velocity, and we're getting average rate of change of velocity. So this is 0.375 thousand feet per minute. The units of the change in y will be thousands of feet per minute. And then the units of the change in x are also minutes. So notice this doubling up in the denominator. That's really common in second derivatives and can kind of mess with people at first. Before I really get into explaining, I'm going to simplify part of this just a little bit for myself. 0.375 thousand feet is really 375, right? 0.375 thousand is 375. So putting it all together, I would say that from minute 2 to minute 6 of this trip, our velocity is increasing by an average of 375 feet per minute each minute. So again, the units of velocity already have a per minute in it. So this is feet per minute each minute. So from minute 2 to minute 3, we expect the velocity to go up by approximately 375 feet per minute. And from minute 3 to minute 4, we expect the velocity to go up by approximately 375 feet per minute, and so on. To look at the average rate of change from 6 to 10, there we have negative 0.25 thousand feet per minute every 1 minute. So again, to simplify that a little bit, I would say that's 250. So this time the velocity is decreasing. So I would say from minute 6 to minute 10, the velocity decreases by an average of 250 feet per minute every minute that passes. All right, so I'm going to jot one of those down. So think about those really carefully. Second derivative interpretations are tricky. So let's write down that second one. So from minute 6 to minute 10, velocity decreases by an average of 250 feet per minute for each minute passed. That's a little scrunched, but hopefully that makes sense. So think carefully about interpreting second derivatives and expect to see those per minute or per minute square, things like that happen. Okay. Next and last part, we want to sketch the graph of this v prime function on the right and think about the meaning of v prime, which is also s double prime. So the first derivative of our velocity function would be the second derivative of our original position function. Okay, so let's just go through the graphical part first, and then we'll get back to the meaning part. All right, so if we want to talk through the slopes of our velocity function, they start off, and again, this is very rough. I already estimated to get this graph, but the way I drew it, it looks like they start off either close to 0 or maybe even right at 0. So I'm just going to say 0 to give myself something definite, but it's kind of unclear. And then the slopes, not the y values, but the slopes are getting steeper as I go. The way I drew it, it looks like the steepest one is somewhere around t equals 3. So they're positive and they're increasing. And then they fairly quickly level back off. And at t equals 4, it looks like my slope is close to or already back to 0. So still positive, but decreasing to 0 in that little section from 3 to 4. From 4 to 8, my slope was 0 all the way through there. From 8 to 10, my slope is always negative. It starts off negative and getting more negative, and then it kind of holds steady, and then it fairly quickly gets a little less negative and goes back to 0. So once we hit 10, we should be back to 0. So it's negative and getting more negative, and then it's negative and getting less negative, which would be increasing. And then from 10 to 12, my slope stays at 0 all the way throughout. So when I'm sketching this second derivative function, so this is my v prime function, which is the same as an s double prime function, second derivative. When I'm sketching this, I'm going to take what I just said about slopes and turn it into a statement about y values. So my y values start at 0. they increased for a while until I hit a maximum, I thought maybe around t equals 3. And then they're still positive y values, but now they're decreasing, positive and getting smaller, and they should get back to 0 right around 4. So this is definitely rough sketch, but just to kind of think through the process again, when you're taking a second derivative, you first take the first derivative, and then you just apply the same techniques to that function you got to create a second derivative. Okay, so from where are we at? 4 to 8. From 4 to 8, it looks like our y values should stay at 0. From 8 to 10, our y values should become negative, and they should get smaller for a little bit and then start getting bigger and make it back up to 0 right around t equals 10. So we're going to go negative, get smaller for a little bit, and then start getting less negative until we make it back up to 0. And then from 10 all the way out to 14, our slopes were 0, so now our y values will be 0. So that is a fairly rough sketch, but that's a sketch of our second derivative function. And that's how we would do that graphically. In terms of a limit definition, we would apply the limit definition to the first function. We would take what we get and we would apply a limit definition to that, and that would give us a second derivative. Okay, last little bit here. What is the meaning of this v prime or s double prime function, and what are its units? So this is what the average rate of change we just did should help us with. Average rate of change gives us an estimate of instantaneous rate of change, which is derivative. So the units should match up. The units should be thousands of feet per minute, or per minute squared, whatever you like. Again, it's shorter to write per minute squared, but when you're interpreting, I think it's good to think about it as per minute. The meaning, this is how fast velocity changes, otherwise known as acceleration. So the meaning of the second derivative of a position function is acceleration. We're going to say s double prime of t, which is equal to v prime of t, can be named a of t, and that is the acceleration function. So acceleration is change in velocity over change in time. I want to be really clear that this will not be the right vocab for starting with something that's not a position function. You'll just have to think through what that is. So I don't want to see the word acceleration unless you started with a position function and took 2 derivatives, or started with a velocity function and took 1 derivative. Okay, that's plenty long. Let's stop there for an intro, and then we will continue in the next video.